Um, Hello, good morning everyone who is watching CINE channel. My name is Karla Andriani and I'm a postdoc at Kitchener Group. And today I will talk about unraveling the first step of methane to methanol reaction mechanism transition metal cluster, which is part of my postdoctoral proposal. And this project also involves other people, some PhD students, master's students, and also scientific initiative students. And so in this short presentation, I will try to address why we should investigate methane to methanol reactions. And in the sense, this presentation is divided as follows, and a brief introduction about the problem. In particular, why we should use natural gas as source of methane, our main goals, the methodology used in this work, some results, and our present work. Why we should use methane, natural gas as new energy? If we look into the graph, we can observe that we are now living in the fourth area of new energies, where not only depend of coal, but also oil, natural gas, and new energy sources, especially renewable ones. And some projections shows that that there's going to be a decrease of, especially on oil and coal, and an increase of natural gas consumption and also new energy sources. So if we look into this graphic, this is an indication that the scenario also is true worldwide, specifically on North America, Europe, Middle East, Africa, and South Central America. But as you can see here in Pacific Asia, they have also a high consumption of coal and oil. So the main goals here is to increase the consumption of other energy sources than these ones on Pacific Asia. So another projection is that the scenario is going to change, and this is a projection of the United States energy, where these countries which are is going to that this change is also going to be almost linear for the OECD countries, but the rest of non-OECD, which are the Organization of Economic Cooperation and in development, including the Pacific Asia, is also has increase. So why is important to use the natural gas? So why it's important to use natural gas? The most important because natural gas is composed by methane, one of the most stable and attractive carbon molecule, which is a precursor of cell chemistry. So, however, the use of natural gas as it is has its limitations, like transportation and liquefaction issues. However, nowadays, when is not born natural gas used by obtaining other energy, other chemicals with high aggregate values, such as methanol. However, the process to obtain methanol is because it's a chemical feedstock, served like solvent, and also a gasoline additive. Nowadays, methanol is obtained via syngas, a synthesis gas method, which is an indirect method, whereas the methane is converted into syngas, which are carbon monoxide and AG2, molecular AG2, at high cost with high temperature and pressure, and with high cost to maintain this these plants. And then a second step, the syngas is surface oxidation to yield methane in different catalysts. Nowadays it uses especially nickel over aluminum, and the second step we use a copper and zinc catalyst. So with different when you use different type of oxygen source, you can lead to different types of oxidation reactions, like the partial oxidation when you use O2, the dry forming, the CO2, and we use water, which leads the steam forming. However, all of them are used in high temperatures and in high pressures. However, also methanol can also, depending on the catalyst, can also lead to full combustion in side products. Another way to obtain methanol is by via direct methods, are called DMTM methods, where methanol in one-step reactions is catalyzed to methanol with different oxygen sources like sulfuric acid, O2, peroxides. This type of different catalysis. This type of catalysis tend to mimetize active site of the the MMOs oxygenized, whereas methanol is obtained from methane in nude conditions of temperature and pressure with high selectivity and with no syngas production. However, this is an unbalanced stoichiometry, and also CH3 can also lead to over-oxidation to CO2, to lead CO2s, and sometimes when you use O2 as a direct fount of oxygen, we know that this is a spin forbidden reaction. So one of the main challenges that regards the transformation of methane to methanol nowadays is because methane is a stable molecule with a tetrahedral symmetry and high pKa. So to extract a proton from methane requires a lot of energy, while this is, the conversions occurs in high temperature. So one of the main goals is to search for more efficient catalysis and understand the whole process from methane adsorption, activation towards the source of the product of methanol or the high value communities. So, however, this is a huge challenge and a complex challenge because we can address at least 4 types of methane to methanol reactions. The first part is the hydrogenation reactions, where methane can use hydrogen for each step to reach carbon, and then carbon can be oxidized to CO. The second part is the indirect reactions, when it can lead a direct product with the same numbers of hydrogen, with the first extraction for hydrogen, and then to lead the products. Then methanol also you have the methanol dehydrogenations as well, that product dehydrogenation in the catalyst surface, and also the side products. We also can obtain the direct reactions. The direct reaction of methanol can lead to the direct products without the extraction of hydrogen. So, however, we also we need to understand how the methane this process occurs on different type of catalysis, and at least two different kinetic modes can be applied to explain this type of reactions. The first one, where all the reactants and products are dissolved on the surface. Or in the catalyst, and the second one, and one of the reactants are in a different phase, in a gas phase. So in our work, we want to understand the decomposition of methane over 3D 13 atoms transition metal nanocluster, where we use of iron, copper, nickel, and cobalt to shed light on the first step of the reaction mechanism. So for that, we use our previous knowledge from this type of clusters, where we obtain the PGMC for the distortion for the pre-atomized molecule by using the cluster dissociation, which yields any Millius configuration of our systems. Then, to reduce these Millius configurations, we use a Euclidean matrix, a second in-house algorithms, to small numbers, in which were applied the DFT, and then which yield our first representative set. Also, to address the effect of the hydrogen co-distortion, we start from the PGMC obtained from the first step and perform the hydrogen distortion as well with cluster distortion algorithm. For instance, for the CH3 we adsolve 1, for the CH3 we adsolve 2 until complete CH4 molecule. Then we have also the second representative set. And to address some cinetic properties, we also performed a step-by-step dehydrogenation, where from the PGMC for the first step we keep fixed the molecule and we abstract one hydrogen atom, which also lead the third representative set. Then with these three positive sets of configuration, we performed DFT calculations using PBE by van der Waals corrections in the light tier 2 with the light 2 base set in FHIM's problem to access some kinetic properties. We use a revised unit bound quadratic exponential potential method, where we can access the magnitude of the activation energy by knowing the adsorption energy of each species, as well the dissociation of the species in the gas phase. However, this is a hybrid semi-empirical method which was proposed in the 80s by Shostakovich. And it also is based on the bond conservation method, and this, as the activation energy directly depends of their distortion, they also sensitive of their sense of DFT level of Turing employed, as well as the van der Waals correction and ZPA. However, despite the fluctuations between the different methods that we can use, this magnitude, this method is faster. It can capture the same tendencies as then Nebby calculations, string calculations, and so on. Recently, this method also was revised by Abdul Pearson in 2018. So here I will show some of our results. We can also observe that then the distortion energy increased the hydrogenation process. As well as a different as well with some established structural parameters change. The increase of the adsorption follows the decrease of the bond length and the increase of the coordination number of CH species, which we it showed that the tendency to carbon to restore the five-fold coordination, as well as the increase of the charge transfer from the metal to the CH species. However, we can also observe that we have the same tendency observed for CH4 to C, where the stronger the distortion occurs for nickels, followed by cobalt, iron, and cobalt, and the last and for copper, the systems on the distortion on copper the magnitude of the adsorption energy for copper are the lowest ones. In particular, for carbon, it's lower than for CH, which also in agreement with experimental observation that these copper-based materials do not tend to form carbon depositions, and while nickel are the prominent one to form this type of deactivation. So the hydrogen, we also perform the same for the two. Here I show the hydrogen co-absorption. We have found that the same tendency observed for the first types of systems. However, we also show that increase the hydrogen co-absorption increase the magnitude of the desorption energy, which can modulate, which is crucial to modulate the chemical reaction barriers. And this is one of our explanations shows that by comparing the two extremes, the nickel and copper distortions, we can follow up. You can see that the increase of the distortion magnitude increase with the broadening of the P states towards the moon, as well as the increase of the hybridization from stage 3 to C of the carbons p orbitals with the d orbitals of the metal. This is not observed. In Kuiper system due to the complete occupation of these states, and also when we compare the introduction of hydrogen co-absorption, this tendency is the tendency of the hybridization of both p orbitals from carbon and now the s orbitals from hydrogen increase the hybridization of the systems with the d orbitals. However, as we can show in the next graphic, in a thermodynamic point of view, nickel tends to form C carbon depositions, while copper, the tendency of copper is not, in this tendency not observed for copper. However, taking stage by taking stage 4 in gas phase as a reference, we also for the methanol obtained from direct methane to methanol, you should expect that nickel and copper should present thermodynamic similar results. However, this is not true for copper atom. And these tables, our house shows that these tables at certain species are CH3 for cobalt materials. So, and how about the cinetic point of view? I will show you the Cooper systems of the 4 steps of hydrogenation process and the activation energy barriers with using ZPA and ZPE and VDW corrections, and without ZPA and VDW corrections, where we can show that the addition of these corrections especially change the first step of the hydrogenation process, since we have the descriptions of better descriptions of the longer range interactions between the CH4 and the metal clusters. However, the same tendency, the tendency of another steps is maintained. And as we show here from the cinetic point of view, of course, the formation of C is also has a great energy barrier than CH3, C2, and C in CH, which also in agreement with previous studies. However, when we look for the first step from our methane hydrogenation, without ZPA and VW corrections, we have this tendency where nickel and copper have almost the lowest energy barrier, followed by ferro, and the highest energy barrier is while copper presents the highest energy barrier. However, when the use of ZPE and VDW corrections, this tendency is changed, with iron and copper and cobalt are present almost the same energy barriers, which is lesser than which is smaller than the nickel, and followed by copper, and this is the same tendency as observed for transition metal sulfurs of these materials. So this shows that this method can be used by a qualitative information with a qualitative information to guide the best catalyst to methane activations. One of our other works in progress is to understand as well the effect of the size on these clusters. So we also study methanol dissolution and the first step hydrogenation on transition metal cluster by include angle 4 to 15, and also you try to understand the dissolution of ordinary molecules on this type of cluster that are common ordinary molecules in syngas process on this type of transition metal nanoclusters. We also have interest in the methanol dissolution and the first hydrogenation oxides, particularly in the first step of hydrogenation, which has been performed by Priscilla on zirconia serial zirconia mix oxides. Part of this work has also been published on PCCP. And we also interested in zircon in the pure oxides, which is being performed by Raquel, the source of transition metal clusters on zirconia, and the same study is being performed by Karina, which in serial pure clusters. So this is what I have to show you about of our previous preliminary results and what we are working on. Thanks so much for watching CINE channel. See you next time.